Okay, so what we're going to do in this, we're going to practice and we're going to discuss some things together. Okay, so the table shows the foot length in centimeters and the height in centimeters for a random sample of 6 high school seniors. Okay, so this table over here is what we're doing. All right, so now what I need you to do is use the Desmos to write the equation of the line of best fit. So you need to actually go on Desmos and type this in, okay, and then we're going to talk about it. But very important, what I remember from last year is some students didn't do any practice and then panicked on a test because they did not know how to type things in and use the Desmos. So understand that during a test or quiz, I'm not teaching you how to do it at that point in time. You have to have already practiced it and you have to know how to do it. So go ahead and type these in. Remember, when we have a table like this, the first column is the X, the second column is the Y. All right, so you type in these data points using the directions that we talked about on this page back here, okay? And then pause the video while you do that and then come back and we'll discuss. Okay, so assuming we both typed this in correctly, and this is one of those things that I'm always nervous about because, one, I don't type well, and also I don't see tiny pale numbers super well, especially on the computer screen. So I'm always checking and double checking, so hopefully I got this right. So again, after we typed them all in, we're going to look at this funny little symbol here to the left, click on that, and that's what's going to make the linear regression pop up. And the equation I got was y equals 3.30769x plus 82. Down below that, I found the R value was 0.8405. And remember, we're not talking about the big capital R squared, just a little r. So now we have to discuss what does this mean in this situation. And what I want to make sure we understand is that as we discuss these things, we need to make sure we relate it to the specific situation. So we're going to use the titles that we are given as we say what things mean. We're not going to just give a generic answer, we're going to give a specific answer. So this particular table compares foot length in centimeters to height in centimeters, so we need to be mentioning foot length and height in just about every one of these answers, okay? So the correlation coefficient is 0.8405, and now keep in mind, what did we talk about? In terms of being strong, okay, so it's a positive correlation, so it's going to be on this side. And remember, between 0.8 and 1 is considered a pretty strong correlation. So a correlation coefficient of 0.84 is definitely going to be in the strong range, okay? So we're going to say that we have a strong positive correlation. Okay, remember, positive correlation means that both increase at the same time. So strong positive correlation as foot length increases, height also increases. And again, I feel fairly confident in saying this, and I feel fairly confident in using this equation because I have a strong correlation, okay? This is sort of my, like my test score, like, hey, are you on the right track? Is this really going to work? If this is a strong correlation, we're going to have a good estimate here, okay? Now, the slope of the line of the best fit, remember, y equals mx plus b, so y equals mx plus b. So when we look in front of the x, that is our slope. So the m value is 3.30769. All right. Now, what does it mean? Now remember, slope is rise over run, and I'm just going to write some things down. So it's rise over run. And remember, it's delta y over delta x means change in y over change in x. So that means we have to understand what's our y value, what's our x value. So change in y, our y value is height. So basically we're comparing height and our x value, and that's in centimeters, to our X value, foot length, in centimeters. Okay, so pretty much what we can do, so this is like over 1, so I'm just going to round it off real quick. I'm just going to say 3.3 to make it simpler. 3.3 centimeters of height corresponds to 1, I'm going to go ahead and put that over 1 centimeter of foot length. So what that means is we basically, remember we're looking at a rate of change. So basically height is expected to increase about 3.3 centimeters for each 1 centimeter of foot length. And we could test that theory. We could, line up, a bunch of you out in the hallway, make you take your shoes off, measure your feet, and see if really every time we get people with 1 centimeter longer foot length than the person beside them, are they actually about 3.3 centimeters higher? And again, we have a pretty strong correlation coefficient, so this is pretty likely to be kind of a reliable measurement. Again, remember, rate of change, you have to compare 2 different units. Make sure you put their labels on them. All right, what's the y-intercept? The y-intercept is the number at the end, and it is 82. Okay, and remember, y-intercept on a graph, right? It's where we cross the y-axis. That's your starting point. So thinking about this, and this is where sometimes scatter plots and lines of best fit are a little bit weird. Okay, remember our x value is our foot length, and our y value is our height. Okay, so technically what this means is if foot length is 0, we're going to be 82 inches tall. Okay, if foot length is 0, person is expected to be 82 centimeters tall. And I'm going to make kind of a little weird face there now because I want to stop and think about this, because sometimes things don't make sense. I want you to think about this. This is a sample of 6 high school seniors. Right? 6 high school seniors. What are the odds that we're actually going to have any high school seniors with a foot length of 0, meaning there's no foot? A foot length of 0 means there's no foot there. So this is really kind of silly, not realistic. All right, and you will see this often in scatter plots, because a lot of times where the data is, like there's a clump of data, and when we go all the way to where the x value is 0, sometimes that's a kind of a nonsensical point that we're not going to have in real life. So in this case, a foot length of 0 is really not realistic, especially, I mean, even if we were talking about babies, they still have some kind of length to their feet, probably, 5 to 10 centimeters, all right? All right, so this is kind of a weird situation, and so sometimes our y-intercepts don't make sense. All right, so now we're going to use the equation to predict the height of a person with a 26 centimeter foot length. Okay, so what this is saying, 26 centimeters, that's saying that the x value is 26. So we're just going to plug in the x value. So again, we have y equals 3.30769 x, so that's where we put the 26 plus 82. And now we're just going to go ahead and use our calculator, which, okay, yep, I have one. All right, let's give it a shot. All right, and we get 167.99994, and I would round that. That makes sense to me to the 0.99999. I'd say about 168 centimeters. And of course, I'm not good with my centimeters. I'd have to convert that to feet and inches to see if it actually made sense to me. Okay, now more practice. All right, so now we have some R values here in red, and we're going to see if we can match those to the graphs. Okay, so I think I'm going to tackle the easy ones first. All right, so let's take a look at which one. Now remember, the number, the R value, tells you how tight the dots are together, not necessarily how steep the slope is. Okay, so let's take a look at my positive values. I'm going to start with, I'm just going to kind of circle my positives. 0.95, 0.175, and 0.82. So in terms of positives, my graphs that are going up, okay, that's going to be C and E and maybe D, okay? All right, so now we want to look between those three, which one has tighter clumps, because the tightest clump is going to have the highest, closest to 1. So I'm going to say this one's 0.95. I'm going to say this one is the 0.82. And I'm going to say this one is the 0.175. All right, because those are pretty spread out. All right, so this is a strong positive. I'm not sure if you heard that. My dog is whining, probably dinner time. 0.175, that's definitely weak positive. 0.82 is also going to be a strong positive. Although not as strong as 0.95. These are really close together, so that's pretty close to 1. All right, now let's take a look at what's the other easy one. So what's left? We have A, B, and F. All right, B seems to be just a jumbled scatter, so I think that's going to be my 0. 0 is going to be no correlation. And then I have 2 that are negative. So A and F, and what I'm looking at is negative 0.88, which is going to be fairly strong, negative 0.71, which is kind of moderate, but not necessarily as tight together and as strong as the 0.88. All right, so let's see. So negative, I'm going to say that this one, since the dots are a lot tighter together, I'm going to say this is a negative 0.88. Strong positive, or strong negative, sorry. And then this one where the dots are a lot more spread out, that's going to be my negative 0.71. And I'm just going to say moderate negative. Okay, so remember, 0.95, very reliable, very strong correlation. We could be confident about that. 0.82 could also be pretty confident with that. Negative 0.8, be confident with that. The 0.175, I would not be confident at all with a linear equation that I wrote from there. And I think this video is over because Danny wants his dinner. So I will see you guys in class.